Hello everyone. Today we will be discussing a topic from IGCSE Cambridge Chemistry, lesson Chemical Reactions, topic Reversible Reactions and Equilibrium. Up until this point, when we talked about chemical reactions, we talked about mostly irreversible reactions, where two or more reactants react together to make one or more products. In this case, when the reactants are over, when they're completely done reacting, the formation of products will also stop. Hence, the reaction will come to a stop. We call it the completion of a reaction. However, there are another type of reactions which are called reversible reactions. In this case, just like how reactants react to form the products can also react with each other, or if it's a single product, decompose to form the reactants again. This would be a reversible reaction. So A plus B gives C and D. C plus D can also give A and B. In this case, we have two reactions, a forward reaction and a reverse reaction. The forward reaction will form the products. The reverse reaction forms the reactants. It's very easy to spot a reversible reaction when the chemical reaction is written down because it will always be indicated by this double-headed arrow. We have one arrow which is pointing towards the right-hand side, indicating the forward reaction, and then at the bottom we have another arrow with just a half arrowhead pointing towards the left-hand side, which indicates the reverse reaction. Whereas in an irreversible reaction, you just have one arrow like this. First, we'll look at the parameter pressure. And pressure will only affect reversible reactions that happen in the gas phase. The products, at least one of the products or the reactants has to be a gas for pressure to be a factor that plays in the changing of the equilibrium position. Now, let's see how this works. Let's look at this example of nitrogen and hydrogen making ammonia gas. Nitrogen has only one molecule according to the balanced chemical equation. Here there are 3 hydrogen molecules. But in the product sides, we only have 2 ammonia molecules. So here we have 4 particles altogether. And in the product side, we have only 2 particles, 2 molecules. So think about it. If you have more products than reactants, would the pressure increase or decrease? If there is more products, that means there's a lesser number of molecules in the system. And if there's lesser number of molecules, what happens to the pressure? The pressure will decrease. Let's recall what pressure really means in a gaseous system. The pressure is how frequently or how often or how hard molecules go and knock on the vessel of the container or the walls of the container. If there's fewer molecules, there will be fewer collisions on the walls. So pressure will be low. But what if there's more reactants than products? If there's more reactants than products, then there will be more molecules in the system than if there's more products. Since there's more molecules now, there's going to be more collisions on the wall. So pressure will increase. If there's more products than reactants, pressure will decrease. If there's more reactants than products, then pressure will increase. Now, keeping that in mind, let's look at how pressure affects the position of the equilibrium. Say we have this system of nitrogen and hydrogen producing ammonia gas. It was nicely in its equilibrium conditions, and suddenly we decide to increase the pressure. This is the change. The change was increasing the pressure. According to the Le Chatelier's principle, always the equilibrium shift happens in a way to minimize the change, the initial change. The initial change is increasing pressure. So the equilibrium shift will happen to counteract this. So the equilibrium will change so that it would want to decrease pressure. So this is what it wants to do. With the equilibrium change, it wants to reduce the pressure. How do we reduce the pressure? So there could be only two equilibrium shifts, either to the left-hand side or to the right-hand side. If the equilibrium shifts to the left, that means the rate of the reverse reaction increase. So more reactants are formed. If the equilibrium shifts to the right, then the rate of the forward reaction increase, which means more products are formed. Now, what you need to decide is how can the system reduce the pressure? Will it reduce if we increase the number of products or the number of reactants? Just now, we looked at the system and we deduced that when there are more reactants than products, the pressure will increase. When there's more products than reactants, pressure will decrease. So what we really want is to decrease pressure. So to do what we want, we need to increase the products and reduce the reactants. And how do we increase the products and reduce the reactions? By promoting the forward reaction. The forward reaction goes from left to right. So the equilibrium has to shift to the right. Okay? When the equilibrium shifts to the right, the products formation will increase. Therefore, there will be more products in the system than reactants. So the system pressure will decrease, countering the initial change. The most common mistake most students do is trying to facilitate the change. Just because they say change is increasing pressure, the equilibrium doesn't change into the position of increasing pressure. It wants to do the opposite. So always remember, what the system wants is the opposite of the change. If the change was increasing pressure, then the system wants to reduce it. If the change was reducing pressure, then the system wants to increase it. You always have to decide the position of equilibrium shifting depending on the want, not depending on the change. The change in the concentration of either one of the products or the reactants will also shift the equilibrium position. Now, for this one, we don't have to think about a lot of mechanics. We don't have to think about the number of molecules or the temperature, nothing. We just have to look at which reactant or product increased or decreased. Let's look at this with a few examples. First, let's take the example of BiCl3 concentration increasing. So the change that happened is BiCl3 equals concentration increasing. This is the change. Now, what does the system want? What the system wants is the opposite of the change. The system will always want to counteract this change. So what it wants is to reduce the concentration of BiCl3. This is the want. This is what the equilibrium shift must achieve. The equilibrium should shift so that it reduces the concentration of BiCl3. Now, there are two ways the equilibrium can shift. Either to the left, or to the right. If you move to the left, if the equilibrium shifts to the left, then the reverse reaction will be favored. The rate of reverse reaction will increase. And because of that, the formation of reactants will also increase. So what happens? BiCl3 increases. And is that what we want? No, we want to reduce it. So that can be achieved by shifting the equilibrium to the right. Because when you shift the equilibrium to the right, the rate of forward reaction increases, which means more products are formed. And when more products are formed, more reactants are consumed. More of these reactants will be consumed. Therefore, when you promote the forward reaction, or when you shift the equilibrium from the current position to the right, BiCl3 will decrease. Now we have achieved our goal. So in a case where one of the concentrations of the reactants increase, we need to decrease that concentration by shifting the equilibrium to the right. Let's look at another example. What if the concentration of HCl increased? Now, this time, the concentration of a product increased. This is the change. This is our change. So what does the system want? The system wants to counteract this change. So the system will want to reduce the concentration of HCl. How can we reduce the concentration of HCl? If we promote the reverse reaction, then the equilibrium will shift to the left. So more reactants will be formed and less products will be formed. At the same time, the products will be consumed faster than the reactants. So HCl concentration will indeed decrease. So if the change was increasing concentration of HCl, then the equilibrium will shift to the left so that it could reduce the concentration of HCl. And finally, we have the last factor that affects the equilibrium, which is the temperature. Now, when we're dealing with the temperature, it is important to know which out of the forward and reverse reaction is exothermic. Always in a reversible reaction, one reaction is exothermic and the opposite one is endothermic. So, in this example, they have said the forward reaction is exothermic. If the forward reaction is exothermic, then the reverse reaction is definitely endothermic. In another case, if the forward reaction was endothermic, then the reverse reaction is exothermic. It's always the opposite. So now let's look at how change in temperature affects the equilibrium. Say the system temperature increase. This is the change. Now what does the system want? The system wants to reduce the temperature, always the opposite. System wants to reduce the temperature. So to reduce the temperature, would it want to promote the exothermic reaction or the endothermic reaction? What happens if the endothermic reaction increases? Endothermic reaction will decrease the surrounding temperature because it absorbs the heat. Because of endothermic reactions, temperature decrease. Whereas because of exothermic reactions, the heat is given out to the environment and temperature increases. The surrounding temperature increases. So if the endothermic reaction is promoted, then temperature will decrease. If exothermic reaction is promoted, temperature will increase. So in an event where the change is increasing temperature and the system wants to decrease temperature, we must promote the endothermic reaction. In this example, the endothermic reaction is the reverse reaction. Since the reverse reaction is endothermic, the equilibrium must shift to the left. What if it was the other way around? What if the change was temperature decreasing? When the change is temperature decreasing, then the system will want to increase the temperature. Temperature can be increased by promoting the exothermic reaction. In this example, the exothermic reaction is the forward reaction. So the forward rate of reaction must increase. Therefore, equilibrium must shift to the right. I hope with this you understand very clearly that what you must do by changing the position of the equilibrium is always the opposite of the change that happened. You have to counter the change, minimize damage. The next part of this lesson, we are going to talk about two essential processes, the Haber process and the contact process. Both of these processes use reversible reactions to produce a valuable substance. First, let's look at the Haber process. Haber process is the process used to manufacture ammonia gas. Ammonia is especially important for nitrogen-based fertilizers. Now, both these Haber process and contact process, you have to know the product, the reactants, the reaction conditions, and the users of the product. First, let's look at the reactants, the raw material for the process. Ammonia is just NH3. So, obviously, the raw material has to be nitrogen and hydrogen. Nitrogen is readily available in air. 78% of the atmosphere is made out of nitrogen. So, nitrogen is taken out from the air. Hydrogen is obtained from natural gases and or hydrocarbons or steam. First, what we must do is purify these nitrogen and hydrogen gases and get pure samples of nitrogen and hydrogen and pass it over a catalyst of iron. It's very important. The catalyst for Haber process is iron. The temperature condition is about 450 Celsius and the pressure condition is about 200 atmospheric. So the three conditions for this process is the catalyst iron, temperature 450 Celsius, and pressure of 200 atm. Then you also need to know the balanced chemical equation for the process. Here nitrogen reacts with hydrogen to give ammonia. If you balance this, you get 1 molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 molecules of ammonia. And to make sure to promote the forward reaction and increase the yield of ammonia, we continuously feed in the gas and we liquefy this ammonia and we remove it. So when you remove the ammonia content, the concentration of products decreases and you keep supplying reactants. So the concentration of reactants increases. Therefore, the position of the equilibrium will always favor the forward reaction. And if there's any nitrogen and hydrogen left, they are recycled in this process. Next, we'll look at the contact process. Contact process is the manufacturing of sulfuric acid. But before we get sulfuric acid, we need to first form sulfur dioxide, and then the second step is to form sulfur trioxide. Then only from sulfur trioxide, we can form sulfuric acid. So the raw materials for this process is sulfur, solid sulfur, and oxygen. First, to make sulfur dioxide, we burn the sulfur in air, and then we have to react the sulfur dioxide further with more oxygen to form sulfur trioxide. Sulfur dioxide burning in air, that is an irreversible reaction. However, the reversible reaction is sulfur dioxide reacting with more oxygen, forming sulfur trioxide. And for this reversible reaction, we have a set of conditions. Just like the Haber process, the temperature condition is around 450 Celsius. but the pressure is just 2 atmospheric, and the catalyst used for this process is vanadium oxide P2O5. Technically, what you need to do is then dissolve this sulfur trioxide in water to form sulfuric acid. But we don't do that. Instead, we dissolve this sulfur trioxide in a concentrated acid instead. Why? Now, this part is important. This is an important safety measure. If you directly dissolve sulfur trioxide in water, a very thick and dangerous, highly acidic mist of acid is formed. And this can be very dangerous to the workers and the surrounding environment. This thick fuming liquid is called oleum, and it needs to then be carefully mixed with water. So the sulfur trioxide that dissolves in the concentrated acid is then called oleum, and that needs to be mixed carefully with water. So this reaction is also irreversible. Water and sulfur trioxide gives sulfuric acid. In the process, sulfur dioxide is formed, and this sulfur dioxide is not a good gas to be put into the environment. It can cause acidic rain, and therefore it is not an emission that we must put just into the environment, must be controlled. Some approaches to reduce emissions of sulfur dioxide in general is given here. Now that we have covered the theory for this topic, let's have a look at a few past paper questions. The equation signifies the Haber process, which changes in the reaction conditions would result in greater yield of ammonia. So we want changes that promote the forward reaction. Let's look at all three statements. Adding more ion catalyst. Now, what is the purpose of a catalyst? The catalyst will reduce the activation energy and increase the rate of reaction. However, does changing the amount of catalyst or changing the catalyst at all change the effect it has on the rate of reaction? No, because what really affects the rate of reaction is just the presence of the catalyst. If it's present, then the reaction rate will increase. If it's not, there won't be. Just because you increase the amount of catalyst, nothing happens. What matters is just the presence of the catalyst. So adding more ion catalyst does not help promote the forward reaction. Increasing the particle size of the ion catalyst? No, that doesn't help either, because like I said, what matters is the presence. Let's look at statement 2. Increasing the reaction pressure. We have one nitrogen molecule and 3 hydrogen molecules giving just 2 ammonia molecules. So in the left-hand side, we have a total of 4 molecules, whereas on the right-hand side, we have only 2 molecules. If we increase the pressure, the system will want to decrease the pressure. And to decrease the pressure, we must go to the site where there's lesser number of molecules. And that is the product's direction. So the forward reaction will be favored if the pressure is increased. Therefore, pressure increasing indeed helps increase the reaction to the forward direction. So the correct answer is 2 only. Let's look at one more question. In the reversible reaction given, the forward reaction is exothermic. What would increase the yield of the product on the right-hand side of the equation? So we know the forward reaction is exothermic, which means the reverse reaction is endothermic. And what we can notice is the all gas, so pressure can affect the system as well. There are 2 molecules in the left-hand side, reactant side, and there's only 1 molecule in the right-hand side. With all that information in mind, let's look at the answers. Temperature decreasing. When temperature is decreased, the system will want to increase temperature. To increase temperature, the exothermic reaction must be favored. And the exothermic reaction is the forward reaction. If forward reaction is favored, then more product PCl5 will be formed. So temperature decreasing is correct. Temperature increasing, now the opposite thing. If the temperature is increased, then the system wants to decrease the pressure. And to decrease the pressures, the system will favor the endothermic reaction, which is the reverse reaction now. When the reverse reaction is promoted, the yield of the wanted product PCl5 decreases. So no, temperature increasing is not helping. Pressure decreasing. If the pressure decreases, the system wants to increase the pressure. To increase the pressure, it will want to shift to the point where there's more molecules. In this case, the reactant side has more molecules than the product side. So again, the system will want to favor the reverse reaction to increase the decreased pressure. Because of that also, the yield of the PCl5 will decrease because now reactants are formed than products. So the only correct answer here is temperature is decreased. That's the only way the yield of PCl5 increases. With this, we have come to the end of the discussion of this topic. Thank you for listening.